In this video, we're going to be talking about the Frobenius method. This is a method to solve a specific category of ODEs. So let's try to construct it up. We want to remember that the regular point or ordinary point of a function f is a point x0 such that the Taylor series of f converges in an interval around x0. So f is analytic as x0. A singular point is a point that is not regular. So we want to focus on a second order, a non-constant coefficient, homogeneous ODE. And we want to study power series solution of this ODE where centered at x0, where x0 is not a regular point, neither of px nor of qx. So the first thing we want to introduce is, if we want to just look at all singular points, we're actually going to be failing. So we're going to restrict the singular points we're looking at, and we say we just look at regular singular points. Regular singular points are specific definition just for the second order non-constant coefficient ODE. And x0 is a regular singular point if x minus x0 times px is analytic as x0, and x minus x0 squared times qx is analytic as x0. If this is not satisfied, then x0 is an irregular singular point, and we are not going to talk about them at all. So why does multiplying by things work? Well, let's look at, for example, f of x being defined by g of x divided x minus x0. Then x minus x0 times f of x is regular at x0 if g of x is regular at x0. In the same way, if we have something like 5x squared divided 1 minus x times 1 plus x, 1 and minus 1 are regular singular points, are regular points, not singular, just normal regular points of f of x times 1 minus x and f of x times 1 plus x, respectively. So when we are introducing a regular singular point of our non-constant coefficient second order ODE, what we mean is that x0 is a simple pole for px. So px can be written as something divided x minus x0, and the quadratic pole for qx. So qx can be defined as something divided x minus x0 squared. So we can write something like that. They roughly behave like that. So we can think of a simplified version of our non-constant coefficient ODE by just replacing px and qx by p0 divided by x and q0 divided by x squared, where we set x0 equal to 0 with a shift. Then we can think that we can just multiply everything by x squared and get rid of the singularity altogether. And now we have a Cauchy-Euler equation. And we know that the generic solution is y of x equals x power r, and we can write an equation to solve for the power r. But that, while it gives us some understanding, px and qx have extra terms. So they're not just defined by p0 divided by x and q0 divided by x squared. They have some extra elements. We have to take care of them as well. So what we do is writing x px as a sum of terms, and x squared qx also as a sum of terms. By multiplying by x and x squared, we get rid of the singularity. We now have analyticity as x. And by a sort of variation of parameters, we take as ansatz, as guess for our solution, that yx is equal to xr times a power series. And we want to solve for the power series. So as before, we write our non-constant coefficient ODE we multiply everything by x squared. Now we know that px x squared is, well, we know that xpx is regular at x0, so px x squared is also analytic at x0, and qx x squared is analytic at x0, so we can use a power series approach in this setting. And we Taylor expand everything. We plug in the power series for p0 and q0 for px and qx, replacing px by p0 plus p1x plus p2x squared and so forth, and x squared q by q0 plus q1x and so forth. Notice that once the ODE is given, then so is the Taylor expansion. Based on the ansatz, we can compute the first and second derivative of y. So they're polynomials, so we can do that. They're a bit cumbersome. You have to keep track of the n and the r in all the places, but we can do it. And we plug this information in our ODE system. So now we want to solve all this for an. You might notice that you can actually write the multiplication of the Taylor series times the first derivative of y and the Taylor series of q times the second derivative of y as discrete convolutions with the appropriate definition of things. And you remember that the sum of that the power series is equal to 0 if and only if each single coefficient of the power series is equal to 0. So we have to check the powers of x one by one in order for the power series to be a solution. And it turns out that for the lowest power, so of r, the lowest power of the power series we are looking at is x at the power r, so n is equal to 0. And the only term that satisfies that is a0 times r minus 1 plus p0 a0r plus q0 a0 equal to 0. We can put away a0, and now we have a term times a0 equal to 0. But we'd like to build up a recursive formula, and we want a0 to be different than 0. a0 equal to 0 gives us the trivial solution. So in order for a0 to be different than 0, then it means that the thing we're multiplying a0 by should be equal to 0. So we have this r times r minus 1 plus p0r plus q0 equal to 0, and this is called the indicial equation, with r being the exponent. And we expect R1 and R2 being two solutions. And then we can go to the next powers of x. And we can define a0 as something, something, something multiplied by a0. So we can solve for once we know a0, we can solve for a1. And once we know a1, we can solve for a2, and we can build this power series. And we can find all the coefficients. When we're looking at the indicial equation, we can have multiple solutions. And this is following quite closely the ideas we had developed while looking at Cauchy-Euler equations. So we can have either the two solutions, R1 and R2, being equal. That on one hand gives us no problem, on the other probably requires us to look at the variational problems, variational solutions. We can have R1 and R2 different, and their difference being non-integers. And this is great because then our two power series are multiplied by different powers of x, and then we're good. They have to be linearly independent. Or we can have the situation in which they're different, but their difference is an integer. In which case it means that one block could be the other block multiplied by x at the power R1 minus R2. And then we have to be a bit more careful. We are not going to be looking into details in case 1 and case 3. We are only being concentrating in case 2. The two solutions of the initial equation being different and their difference not being an integer.